Okay, so now this is part D. Let's try plotting G equal 1 over S plus A. So it is pretty much the same as the previous one. However, at this time, um, instead of 0, is at S equal minus A. Now Paul is at S equal minus A. So the denominator, it's similar to what you saw before. It is just 1 over that. So G of J omega, where you replace all the S's with the J omega, this is what it's saying, 1 over A S plus over A when frequency J omega is much higher. So what happens, what you're trying to find is what happens to the whole magnitude and what happens to the phase. Phase is pretty much now at minus 90, but your magnitude, so this is what you're doing with the calculation right here, and it is multiplied by 1 over A. These are the absolute value of it because that portion is your M and this portion is your phi. So anything that's on numerator, you're adding. So this is a plus 20 log 1 over A, and anything in your denominator, you subtract. So 20 log omega over A. What are we doing in here? So if your omega is high, what happens? If your omega is low, what happens? If you look at the overall equation, 20 log the magnitude, we'll look for what's this and what is this. So it is pretty much exactly the same graph, but in log scale, and that's your M, and for your omega, you will end up having something that goes all the way to 1 for the normalized one, and then you'll have 20 dB per decade drop. This is your asymptote. For a real graph or real value, you will end up looking like something like this with approximately minus 3 dB down. You know that Bode plot for just a single 0 at origin, where S equals 0, you will have G over omega, which is purely J omega. It only has high frequency asymptote. There's no low frequency element. So for the high frequency asymptote, it starts 1. So pay attention to scale on the x-axis, the horizontal, y-axis, vertical, whether it's a 20 log m or the 20 log m over a. If it's divided by a, that's normalized. If it's not, then it's just a regular plot. So starting at 1. And for any s on your numerator, your phase degree is 90 degree. Look at it, 0 plus j omega. So 0 over j omega, as j omega is right here, and that is 90 degree. Moving on to example of g of s function, which is 1 over s. It has a pole at 0. The 0 means like a numerator 0. And then it's the same thing that you place 20 log of absolute value, 20 log of 1 over a minus 20 log omega over a. And then you will end up with minus 20 log a. I'll do a quick calculation for you. So that's the same as 20 log 1 minus 20 log a minus 20 log omega, that is 1, minus 20 log a. So this cancels out, and 20 minus 20 log a plus 20 log a cancels out. That is 0, and you end up with minus 20 log omega. Let's quickly work on g of s equal s plus a plot for it. So now we are, pay attention to this, is log m over a and frequency over a. So earlier I may have said this is log normalized. So 20 log m, it's not the whole thing over a, but only m over a. And this one frequency is omega over a. So when omega is a, omega over a is 1, and that's what this one is presenting. So again, so that will be point of your interest, and it will start at that point. That is, I'll draw in a larger and thicker line. So that, if I kind of do this, is going towards here. So 1, that is 20, that is 40. So every 10, you increase by 20 dB. 100, you increase by 40 dB. And that is looking like this. And interesting happens at that frequency, exactly 45 degree. That's where it is. So I'm going to represent this as more of a guideline right there, and the blue one as actual asymptote. And then when you draw it, there will be 1 decade before, 1 decade after of your interest. Straight line through the 45 degree before it's 0, after it's 90 degrees. It's a similar 1 over SA. We have a calculated magnitude and the phase. So right there, and 20 dB down, and then you have something interesting happen at minus 45 degree, 1 decade before, 1 decade after. It starts at 0, downwards. I'll go a little more straight, and then at minus 90. Now let's do actual example. Now we'll plot something for first order factors. So you're familiar with this diagram? It's unity feedback system with fourth path. You have a G of S, and we are representing G of S. These are something you have solved before. K times S plus 3, so there's a 0 and minus 3, and over S plus 1, and S plus 2. So there's a pole at minus 1, pole at minus 2, and this is 0 at plus 3. And this one, maybe I'll draw it like this, although I'm just pointing at it. and there's your S, and system 1 type transfer function. For you to draw a Bode plot, first thing you do is rearranging it so that your writing will be in terms of S of something, and then +1, +1, and +1 in this format. So let's try the calculation. These are step by step, but you'll be able to. We have done this one before, but I'll repeat here. So you have a K, but now you want to divide, have a 3 out there. So S over 3, that will still make it S, plus 3 over 3, and that is 1. And then underneath, you have S, S plus 1. It's already in that form, so it's okay. And then it doesn't require it, that's okay. But next one is S plus 2. So we divide by S plus 2 divided by 2. Since you divide by 2, you have to multiply by 2 for it. Okay. So you end up with 3k S over 3 plus 1 over 2s, s plus 1, s over 2 plus 2 over 2 is 1. So you get in this format, and then you put this together, and that's how you end up with 3 over 2k s over 3 plus 1, just s plus 1, s over 2 plus 1, which is the same as this. So I took over the G of S from the previous page so you can see it as your reference. And then let's find out what happens to each item. So first thing first, we have 3 over 2 and S. S is pretty much from 0 and then downwards. So it would have been 0 downwards like that. I'll draw in better. So originally it will be 1 over S starting at 0, literally. And then as you saw, that would have been from here. I wanted to use this one again. From here, 1 deca, 2 deca, and 3 deca, minus 20, minus 40, crossing minus 60. But it's been shifted up by how much? Where is it starting? That's starting at 3 over S. That's why this is combination of this 1 over S term and where it's starting 3 over 2 in terms of the absolute value. So 20 log 1.5 is 20 times 0.176. So that is about, so let's look at it. Log 3 is 0.477, log 2 is 0.301, log 3 over 2, that's what we're trying to get, is log 3 minus log 2, numerator minus denominator, 0.477 minus 0.301 is 0.176. 20 log, so you multiply by 20 literally, 20 log of 3 over 2, it's a 17.6 dB. So let's just finish up. So something interesting happens at 1. And something happens at 0. And something happens at, I'm going to just draw like this. And something so meaning at 1 it's going down because it's all in denominator. And this one, something happens at 2. So 1, 2. So right there at 2, we have another decay coming up here. So something happens at 3, 1, 2, 3. And then you will see this original blue line. That is 0, 0. So it's a plus 20 dB per decade. And this portion was taken care by this portion originally. And of course, for frequency response, over sweeping of a frequency up until 1, it is minus 20 dB down, and so it was originally going like this, and then you have another forcing to keep going down, so now it is 40 dB per decade, and then you have another one starting right there, so it gets a sharper edge drop. It's a 60 dB down, and until the 3 where 1, 2, 3 0 is introduced. 1, 2, 3 0 is introduced. It's going back to minus 40 dB per decade. You didn't see any further not like that, but any other interceptable. Maybe that will be 10, that will be 20. If 20, there was a pole at 0 at 20, so if you had S plus 20 term on top of the previous one, and that will some interesting would have happened. So this is your Bode plot, and that would be summary for due to pole at 0, that's S, pole at minus 1, S plus 1, pole at minus 2, S plus 2, 0 at minus 3, it's on the numerator S plus 3, and you just check what happened to the frequency at the start. At 1, something significant happens, and 2, 3. So pretty much port 2, port 3, it's your client. And you still have a pole at 0. So you tally up all the pole, you subtract all the poles, and then you add 0. 0 happened to happen at 1, 2, 3. 3 instead of graduating later, this is graduating then at that time, and this is what you have achieved. For the Bode plot, phase angle, it's a little trickier, but it's always around plus 90, minus 90, minus 45, and plus 45. So let's just start with the first one. Pole at, if it's just a constant, 3 over 2 right there. And you have pole at this one is something. It's 0 is at 45 degree. So right there, 1, 2, 3. So that's what something will pass through. And then you draw a line before and after until it meets 0 and 90. Similarly, you take care of other ones. So at 2, what will happen? So that's what we are looking at. At 2 again, that is at 2. And then see this, and see this minus 45 passing through. So this one, minus 45 passing through will look like 1 decade before, It passes through, and 1 decade later, plus and minus. So you continue to build these in this matter until you have spoken to all the lines. When you do finally combined, you had 1 over this one, and then you have another one here, and you have another one here. That was a 3, and this one was a 2, and so on. You can smooth out by adding those lines into actual magnitude. There's a bit of that. Minus 45 per decade, minus 90 per decade, and etc. In part E, we'll move on to second order Bode plot for low frequency.